Welcome to a new episode of our SECED podcast. I am Maria Liapopoulou and I am an 1851 Brunel Fellow in Engineering at the University of Cambridge, and I will be the host for this episode. I have the pleasure of welcoming today a distinguished guest, Professor Michele Calvi, who will share his experience on earthquake engineering research and practice. Professor Calvi is a professor at the University Institute of Superior Studies in Pavia, Director of Science of the Eucentre Foundation, Italy, and Executive Vice President of the International Association of Earthquake Engineering. Having been active in innovation in seismic design, both in research and practice, his experience spans from masonry and reinforced concrete buildings and bridges to displacement-based design and seismic isolation. Professor Calvi founded the Eucentre Foundation and the Rose School and co-founded the Journal of Earthquake Engineering, is an author of many publications and notable books, including The Seismic Design and Retrofit of Bridges, Displacement-Based Seismic Design of Structures, and also an invited keynote speaker in many conferences, including 2 world and 4 European conferences on earthquake engineering. Professor Calvi has been designer, consultant, or checker for various structural projects, including the Rion-Antirion cable-stayed bridge in Greece and the new housing system after L'Aquila earthquake in Italy, for which we will talk more later. So hello, Professor, and thank you very much for accepting our invite. It is a pleasure to have you with us today.
Hello, it is my pleasure, and thank you for the beautiful presentation.
So I would like to start with your journey into engineering, and let's go back to the very beginning. How did your interest in civil engineering begin? Was it something you always knew you wanted to pursue, or did it come from a particular experience or influence?
Well, if you are talking about civil engineering and not specifically seismic engineering, I have to tell you that essentially I grew up in a design firm. My father was an engineer, and since I was a child, I was, running around the legs of people working on technical drawing schemes and so on and so forth. So somehow I grew up in that atmosphere. Probably I was more fascinated by architecture than by civil engineering at that time. But then, of course, you're not always allowed to make any choice. Often, life is making choices for you.
I see, yes. So there was always this influence, and then it came natural. And
Yeah.
what about earthquake engineering specifically?
Well, earthquake engineering, I would say that on one side, when I was finishing my high school and studying at the university, there were in Italy 2 major earthquakes. One was 1976 Friuli earthquake with more than 1,000 deaths, and the other one was in 1980 in southern Italy with more than 3,000 casualties. So these were 2 events that were in my, say, formation years, and therefore were impressing myself a lot. But I have to say that, again, it was life making a choice for me, because when I finished my first level university degree, I applied to several American universities, and then I decided to go to Berkeley, and it was impossible not to become a seismic engineer studying at Berkeley.
Yes, so I want to come to this point. You spent a year doing an MSc there, right?
Yes.
What was the experience like? How did it differ from what you were used to in Italy, and how did you decide to go there?
Well, again, the case, fortune takes a lot of relevance in this kind of choices, but to say about Berkeley was somehow magic for several reasons. One was that Berkeley was permeated by this flavor and image of a place where revolutions in the way of thinking and the way of teaching had been taking places in previous years. The other aspect, which was fundamental at the time, was that the faculty in structural engineering and more specifically network engineering at the time was incredible. My professors there were Ray Clough, Vic Bertero was also my advisor, Joe Penzian, Scordelis, Ed Wilson, Graham Powell. I could go ahead with a long list of incredible names that were all at the same place for that not so long period of time, making an incredible environment to study and to learn and to be fascinated by the people who you were in contact with.
Mhm. So I guess that after that, the decision to pursue a PhD was somehow natural for you.
Actually,
Uh,
this is a bit different. I was already admitted in a PhD course at the Politecnico di Milano in Italy.
uh-huh.
That was one of the reasons why I stayed only for 1 year and that I did not continue for a PhD at Berkeley. It was because I was already in a
Mhm.
PhD program in Milano. So it's the reverse, let's
Oh,
say.
I see. And then you went back to Italy. So after a year to do your PhD, what was your PhD experience like?
Yes, I came back here and I finished my PhD shortly after my experience in Berkeley because, as I was saying, I was already enrolled in a PhD program. That was also a great experience. Also in Milano at that time, there were great people, and to come back with this, say, let me say, new experience in dynamics and in network engineering that was not that deep in Italy at the time was a great opportunity to put together the advancement in say mechanics and finite element analysis with seismic engineering and design. But after a few years, I went back again to the United States, and I taught at the University of California, San Diego. Uh, After having met the person that I've been working my entire life, was Nigel Priestley, who had moved to San Diego in 1986 from New Zealand. New
Mhm.
Zealand at the time was another incredible place. You may remember Pauly and Priestley, the three Ps, and their
Of
books.
course, yes.
The first book by Pauly and Priestley, published in 1973, that became a masterpiece and probably the beginning of a new era in design of concrete structures. I met Nigel in the US, and somehow we felt to be on the same way of thinking. He was much older than me, but not so old that we could not become friends.
Mhm.
And after our meetings in the US, he came and visited me. I was a young assistant professor. He visited me in 1989 here, and then I went for a sabbatical to San Diego in 1990.
Mhm. So you would say probably that he was a mentor for you, the person that maybe inspired your approach
Yes,
to
but
engineering, or
but
if you can name other people as well.
yes, I could name other people, but he has been more than a mentor because he has become a friend. So he was a mentor, but close enough in age to work together and not just information was information and knowledge and culture and competence was not going in one direction only.
Mhm.
Um, but yes, he has been probably the most important person in my academic life. Another
Okay.
person that I would probably name is Professor Paolo Pinto from the University of Rome, who was a few years older than Nigel. Uh, Between Nigel and me, Nigel was born in 43 and I was born in 57. So between Nigel and me, there are 40 years, 14 years of difference. Paolo Pinto in Europe was certainly the leading person in seismic design. He was the chairman of Eurocode 8 and say another very inspiring person.
Mhm. How was the first time you started your work as assistant professor, firstly at Pavia? what was inspiring your research? What was your main direction at the time?
I was very lucky. I was very lucky because my former professor at my first degree in the university, Professor Giorgio Macchi, uh, uh, was very happy to have me back as an assistant after these few years. I'd been, say, traveling and spending time elsewhere and so on. And somehow he protected me and he left me to work completely freely. So he was, he had the perception that he was not an expert in seismic design. His field of competence were different, were design of bridges, were nonlinear response of structures, and so on. And he left me completely free, and he protected me, and he allowed me to create the perfect situation to grow and to create sort of a school. So at the time, I was mainly working on masonry and concrete structures, but I was somehow then starting working on bridges and taking all what I studied in earthwork engineering into these fields of competence.
Mhm. And then let's go to the 2000 when you founded the Rosa School, the European School for Advanced Studies in Reduction of Seismic Risk. The Rosa School in Pavia offers master's and PhD programs with an innovative teaching model. You are offering intensive month-long courses rather than the traditional semester courses in parallel, and this allows for world leaders in earthquake engineering to teach there, with students and faculty being international. So I'm curious to know what inspired this innovative approach and what was the vision behind the Rose School.
Yeah. You did well. You have been studying a lot what happened, and you are also right about the timing. Let's say that there are two issues there. One issue is that I started thinking, how was it possible to somehow repeat an environment similar to what was my experience in Berkeley of about 15 years earlier? And my conclusion was that it was impossible to put together a group like the group that was at Berkeley at that time, in my opinion, was something that would never be possible in the future. And I started discussing about these issues with Nigel, and we came out with this idea of having the courses in series. And the reason was that if you have courses that last 1 month and you are fully committed to that course only, then it is possible for any very important people to come for a month. And we set up a program where the idea was that the person was committing to come 1 month every 3 years. So we started talking to our friends, and this was very important because particularly in the first years, all professors at the Rose School were friends, where they were happy to come. And actually, for some time, they were asking, "Are you crazy to spend all your time and all your, intelligence and so on a school? You're not in this way. You will produce less papers. You will produce." And at the end, they agreed. At the end means a few years later that it was a great idea, and that actually this was probably also a very rewarding academic experience. And at that time, we had friends coming from Japan, from the US, from New Zealand, from everywhere, let's say, and they were coming, and it was not only a kind of a school, it was a kind of academy where people were happy to come. And after the first year, in which of course things had to move slowly, it was a great success in terms of capacity of attracting students. And this is not surprising again, because when students were seeing that there were so many famous names all available in the same place, they started really to come. And there were years in which we received more than 1,000 applications, and we never accepted more than, say, 20 or 30 or something like that. So we were not looking for large numbers. We were looking for a particular kind of relations between professors and students. I remember that at one of the very first meeting of in the founding time of the school, we had a meeting with experts coming from the World Bank, were telling us about long distance learning and all this. It was the time of these new projects where it was possible to experience courses from far away and so on. At the end of the presentation, one of the professors were already accepted to come to the school. Mike Collins, who was a New Zealander teaching in Toronto, raised his hand and said, "Oh, I have two notes. One is that these kind of things always existed. They were called books." And the other comment was, we want to do exactly the opposite. We want to have the students here and to have a continuous contact between professor and students. So in a way, it was a great success, and I think it was also a very rewarding experience that lasted for sure until Nigel's death in 2014. And of course, the school still exists, and now has become, say, more traditional. But what is very interesting today is that the connection among former students is very strong, and there are former students of the school teaching in many universities around the world. And it is always a great pleasure to see at the great conferences, the World Conference, the European Conference, to see that the party of the Law School is by far the most attended party of the entire conference.
Mm-hmm. So, as you mentioned, and according to my information, today, 25 years after its founding, you receive over 1,500 applications per year
No,
from,
today is much less. Today is much less. Today is much
okay,
less.
from
Today, I
different countries, yeah?
Yeah, from different country, yes, but the numbers are smaller. I cannot tell you exactly the figure because let's
Mm-hmm.
say that other people are taking care of the school and not directly me. But I would imagine that we today have a couple of hundreds or something like that applications per year.
Mm-hmm. So my question on that is, what would you say is needed for someone to have a successful application?
Say it again, what?
What do you think is needed for someone to
Oh,
have a
it's needed.
successful application?
Ah,
What are you
ah.
looking for?
Oh, I see. I see. Well, I wouldn't say that nothing special is needed. Of course, we go through interviews we go through say a selection process in which there is a first selection where someone is looking into papers essentially. So it is necessary to be a good student. But what is very, very important is to have someone which is known to us, who writes a letter and says, these students is worthwhile to be a student of the law school. The reason to trust this is that uh, if a known professor is writing something for a student, he's somehow putting his word on that. He doesn't want, I mean, the student is somehow committed to the fact that that professor will somehow guaranteeing about his profit, his willing, and so on and so forth. After the first phase, we go through interviews of all prospective students, and we come out with a classification. During these interviews, I would say that probably it's more important to show the capacity of reasoning than a deep knowledge in all possible fields. So we like very much to go to first principles and to see how someone can resolve, not necessarily to find students that are already experts in seismic engineering. We will teach them seismic engineering, but we want to see people that can reason fast and give us the flavor of being someone that is promising to become not only a good student but a good researcher and a good professor in the future.
Mhm. Yes, this makes sense, absolutely. And how do you think this system affects the learning experience for the students? Do you think there are advantages in being focused on one specific course from the part of the
Oh,
students rather than
I
having to deal
see.
with things
I see,
simultaneously?
understand your questions. Actually, this approach had been criticized at the beginning. There were people who were telling me that 1 month was not enough somehow to go deeply into something. but our experience is completely positive in the sense that in a normal context, you maybe are following maybe 4 courses and maybe for say 3 or 4 months, something like that. So let's say that the, the, the total is the same. But when you have that month, what happens is that you are always facing the same professor. The professor is fully dedicated. Also, professors are coming from elsewhere. And in those weeks when they are here, they can afford to devote their time almost completely to students. And students are having lectures, are facing lectures almost every day, and doing their homework assignments during the weekends and working at night. So it's a different experience. Is a full immersion experience. And our experience is that good students are very happy with this kind of way of teaching.
Mhm. Great. Okay. So let's go now to 2003, when you founded the European Center for Training and Research in Earthquake Engineering, Eucentre in Pavia. The center has since become a major international hub for seismic research, engineering innovation, and training, and is known for its excellent academic output and world-class experimental facilities. So again, I want to ask, what was the motivation behind this, and what were some of the challenges at the beginning?
Yes, 2003 is correct, and it's not a number like another. What happened is that in 2002, at the end of October, there was a small earthquake in Italy, in southern Italy, in which essentially only one building completely collapsed. This building was a school, and in that school there were 27 children that died. So it was something that moved a lot the public opinion. It came out that the seismic code was older, the seismic classification, the hazard map was not updated. At the time, I was the head of the most important commission, scientific commission consulting for the government. And I chaired the commission who wrote a complete system of new codes in 3 months. When these codes were adopted, the adoption came through an ordinance of the prime minister. And in this ordinance, I convinced the people who were relevant decision makers in the politics at the time that there was a need of a laboratory, which was not a university laboratory where everything is difficult, the money is never enough, the competence is let's say, diverse. And this was the starting of Eucentre. So they put a few millions, not a large amount of money, and I created this new laboratory very fast. Actually, the first large-scale experimental facility opened in September 2005, so in less than 2 years. What happened after that is that there was a very strong link between the school and the facility. So on one side, there were an availability of very good students. On the other side, the youth center started making a large number of tests. And what happened is that in a short time, the level of knowledge, the level of competence of the technicians grew enormously. Most of them were former students who accepted to remain in the system as researchers and experimental people. And the youth center did not receive any further public funding, but competed in research grants and competed in all sorts of say possibility of getting research funding, but also made a lot of testing for the industry. And today, I don't think that there is another say semi-public foundation or institution in which there is a similar number of tests performed every year. At Eucentre today, more than 300 large-scale tests are performed per year, which means that the capacity of the people working there is enormous. And actually, there are big companies who are producing shake tables, whatever, who are asking us to help them in testing and in mounting the facilities elsewhere and providing competence to the local people and so on and so forth. Today at Eucentre, I believe that there are about 120 or so researchers. The present president of Eucentre is one of my former students, Rui Pino, and I fully trust him as one of the best researchers of his generation. And again, between me and Rui, there is about the difference of age that there was between Nigel and me. So I think that about 15 years is a good difference to be able to transmit competence, not being too far in age.
Mhm. Great. And among the projects that EU Center has been participating in, one of them is the Mediate project, which deals with multi-hazard risk. And in general, the center has shown a commitment to responding to current challenges
Yes.
related to this increasing complexity of hazards, such as considering multi-hazard or climate change. So I am curious, how do you see these challenges in general? How does the earthquake engineering community
Yeah.
needs to deal with that? And what is the role of the center specifically?
Yeah, you are perfectly right. Eucentre started with experimental activity, but soon after that there was another large branch that became very important, which is the branch of databases and data treatment and data analysis. So Eucentre is now the center of competence of the Italian civil protection, in which all data related to, say, schools, sports, airports, hospitals, bridges. There are in the database there are more than 20,000 bridges or more than 50,000 schools and so on and so forth. And Eucentre started developing algorithms to a quick say provision of what would have been happening in case of a strong earthquake. So the civil protection is counting on Eucentre to know in say within 1 hour after a strong earthquake which bridges could be used, which hospital could be assessed, and so on and so forth. This is part of the context that you were describing. The other issue is that a few years ago there was a call for proposals from the OECD for a facility to produce a global earthquake model. And at that time, the Italian government accepted to ask us, me in particular, to compete to get these projects. And so the GEM Foundation was driven to come to Pavia. And as you know, the GEM Foundation is today leading in the field of asset and risk model. So Eucentre, the Rose School, and GEM, the Global Earthquake Model Facility Foundation, are somehow living in the same place. And this is facilitating a lot relations among these different fields. For what concerns the future, again, you're right. There is this increasing need of multidisciplinary facing of problems. One significant first, answer to this point was that the last large project I coordinated in Europe as a deputy director, again, another student of mine, now associate professor Gerald Regli, was a program named IRIS, in which a significant part of the program was devoted to wind engineering. And you say, what's the relation between wind and earthquake? Well, dynamics is dynamics. And actually, I've been pushing in the last years up to now without much success, but I believe that another area where there is a need of multidisciplinary approach is the area of, let's say, blast. Blast is not only military issues, but is also, so it could be a ship against the pylon of a bridge. It could be an airplane against something, and so on. And I think that this is another field in which in the future we will assist to great developments.
Yes, you're absolutely right in that. Okay, so let's go now to some consulting projects that you have worked on. You have contributed to many construction projects in various roles, and I'm curious to know what were some of the most memorable projects in your career.
Well, you have mentioned when you opened this interview the Rio Antirio Bridge, which has certainly be one fascinating and great experience in your country. So probably you know it well. For me, it was an extraordinary experience also because again of the people who were involved. In that bridge, I was part of the checker team. We were a very small group of people working for the Greek government. But in addition to Nigel Priestley and Frieder Seibler, there was Ralph Beck. I don't know if this name sounds familiar to you, but maybe if I say it, Terzaghi Peck, the famous book on geotechnical engineering, this could ring a bell to you. Ralph Beck was one of the most famous geotechnical engineer in the world, and I was also part of the checker team. Another person was Riccardo Dobri from the Rensselaer Polytechnical Institution in the US. So for me, it was another opportunity of growth. But more than everything else, it was an opportunity of working together with very, very experienced and good bridge builders. We were more focusing on earthquake problems because clearly the experience of designer constructions was more focusing on, say, civil and structural engineering. And it was fantastic. It was, to have to deal with all these complex construction technologies, the construction of the foundation in the wet dock, in the dry dock, and then the movement to the dry dock, and then so on and so forth. It's a long story. I cannot now enter into details, of course, but it has been a great experience. If you want to mention other projects, I could mention the intervention on the Anatolian Viaduct in Turkey after the 1999 earthquake, the November one, not the August. There were two big earthquakes in 1999 in Turkey. This was a viaduct of 119 spans, and Nigel Me designed the system to raise up the entire bridge and move it and to make it shorter of 1.5 meters. So again, it was a thinking about technology, and we made it continuous, and it was very, very interesting. The project in L'Aquila that you also mentioned, it was incredible for other reasons. I managed to conceive and construct 186 buildings in 6 months. And in these 186 buildings, it was possible to recover, say, permanently, almost 15,000 homeless that resulted from the earthquake. Actually, at the end of the earthquake, the homeless were about 3 times that number. But as you can imagine, many of them found other ways of living. But at that time, there was a lot of discussion because people were saying that there was not need of new construction because the timing would not have been reasonable, so on and so forth. But actually, what happened is that most of these buildings have been used until now. Well, let's say for something like 15 years or so. And now, just recently, they started the procedure in which a few of these buildings will be used for different purposes. So I believe that this is something that at that time was all invented in a few days, but I believe that in the future it would be intelligent to think in advance about what to do in case of a strong earthquake.
Yes.
Um, I don't know if you want more experiences. I could go ahead forever. Up to
Yes,
you.
it's very important what you say to consider also the future use of buildings. I want to
Yes.
go back to the Rio Anterior Bridge just
Yes.
to have a bit more of discussion on that. So this is a project, just to mention for our listeners, to give some background. It's a bridge spanning nearly 3 kilometers across the Gulf of Corinth, with 250-meter tall piers and main spans of 560 meters. And as you mentioned, this is a very challenging project. It's in a very seismic area with deep water and soft
Yes.
soil. So could you give us some details on the level of innovation, the solutions you needed to
Oh, yes.
use there related to these challenges? What
Well,
is your
well,
your
first of
approach? Yeah.
all, the bridge is founded on piles because, as you were saying, the poor condition of soil at 70 meters depth in the sea. But there is no continuity between piles and foundations. So the foundations are sort of direct foundation on piles that more than piles, we were calling them inclusions. This was an idea of a good friend of mine, Alain Pecker, who is a geotechnical engineer from France. We worked together in another project. And what they were proposing was to say insert these piles about say 2 meters diameters and maybe 40 meters long in an area which was approximately 100 by 100 meters for each one of the piers. So inserting them, it was a way only of confining soil because you were not excavating soil, you were adding material. And therefore the soil included between these inclusions was somehow confined by this inclusion. And it was possible to do this from the top of the sea, so without any man working down there and so on. The additional advantage that we were trusting yes and no, but we were listening to our geotechnical colleagues was that in this way, say an ultimate level of protection of the bridge could have been the possibility of the foundation to slide and rotate on the piles. So on top of the piles, there is about a layer of about 3 meters of carefully selected sand and gravel, so that in extreme condition, rather than having something worse, the bridge could, the pier could translate and rotate on the foundation. Then the piers are very massive, but they were the construction was started out of the water in what was called a dry dock, which was an area somehow excavated and protected about 12 meters under the sea level. Then this area was flooded. This part of the piers were floating, and then they were carefully moved to the final position, and the construction was continued, and the pier were synced into their final position. Again, something not so common. The next interesting thing is that when you are dealing with a cable stayed bridge, you may have noticed that it's more familiar to see piers in the part which is out of the water, in say above the level of cars and of the spans. It's more common to see only 2 columns. In this case, the designer of the non-seismic part were willing to have 4 columns to increase the stiffness in the in-plane direction. The stiffness of the deck is fundamental to reduce the vertical displacement of a span of 562 meters long, as you were mentioning earlier. But if you think in terms of seismic problems, and you imagine to have 4 legs, like something like this, and you imagine to have a certain neutral axis, you can conceive that you have one of the 4 legs in compression and 3 in tensions. So in a situation like this, in one leg, you have 4 times the initial compression plus the tensile capacity of the other 3. So if you start with something which is, say, 20% of the capacity, then in the compression leg, you have 4 times 20%, which is 80%, plus the tension capacity of the other 3. So you are close to the capacity in compression, which means that you have no ductility, you have no deformation capacity. So we have to convince the non-seismic designer that it was better to increase the concrete size, to reduce the average compression, and to reduce the steel, to reduce the tension capacity of the other three columns. I'm trying to explain this in very simple words. I hope you can understand what I'm trying to describe. A final
Yes, I
issue which
see.
is very relevant is that when you deal with a cable stayed deck, you can imagine that the deck is hanging from the top of the tower, and therefore is acting like a pendulum with a very long period of vibration. Essentially, very little seismic problems, very long period of vibration. But in this case, the relative displacement between the deck and the columns could be very large, not acceptable. So you need to reduce this displacement. If you fix the deck to the columns, then you have very large force because the entire deck mass will be fixed. Active mass will become a mass at which you apply the inertia force, the spectral acceleration. So the solution was to use dampers and to connect the deck to the piers with dampers to try to control both the displacement and the force in the dampers. But now you have something that could move, and at that time we were using hydraulic dampers. And if you imagine that a damper is moving with a very small movement, every time a car on the track is passing on the deck, then it will be unavoidable to have some sort of leakage between the piston and the part in which the piston is moving. So the solution again was to have a kind of an additional element in which there is a pin, a steel pin, that keeps the deck rigid with the pier. But as soon as the force goes beyond a certain level, the pin breaks, and then the four dampers are starting working. So this again is a situation in which you have some small damage, easily replaceable, and the seismic problems will be controlled. As you are saying, it's a highly seismic prone area, so this happens already 2 times. So if we should start now a long discussion, we could discuss for which level of return period you could accept something like that. That will of course imply some intervention of the bridge, possibly some temporary closure. But then we should also discuss for which level of return period you will accept some relative movement between the foundation and the soil. So what I'm trying to say is that this is a fantastic experience to discuss what is the correlation between the losses in terms of direct losses, but also in terms of indirect losses, closure of an important bridge like this one and so on, and the return period of the event you are considering. Is this enough for the time being?
Yes, this is more than enough. Thank you very much for providing the details of this project. And if we go now back to L'Aquila,
Yes.
one thing there is, as you say, that there is a time constraint. You need to come up with a rehousing solution in a very short time, and there are a lot of uncertainties in the design. So how challenging is it to design these houses with all these unknown parameters, and what assumptions or conservatism you need to take there?
It's a great challenge, and there is the interest of someone who is curious as I am. So the solution there is relatively simple, as it is almost always the case, and that is to try to make the response as insensitive to parameters as possible. So that's why all those buildings are isolated. We use more than 7,000 isolation devices. At that time, it was not so common to use isolation devices for this purpose. And in a way, the idea was to tell all sorts of different kind of construction companies use whatever material and design concept you're used to. Use concrete, use steel, use masonry, use timber. We do not care too much. Do not go through complex, say, seismic analysis or nonlinear seismic analysis. We only want you to show us that you can take 10% horizontal of the mass as a force in the horizontal direction. So like designing for point 1G. We take care of the rest because we will use friction sliders, and sliders will be designed in such a way that we avoid to have a transmission of force which is more than 10% of the gravity load, because putting together say the pendulum response together with the friction coefficient, we cannot go beyond those levels. So in addition to that, we designed two different plates, concrete plates, so that the lower plates made the solution very sensitive to soil condition, so very uniform and relatively low force. The second plate reduced again the uncertainty in the response in the upper building because of its mass, very relevant with respect to the upper building. In between the isolation devices, all the system we were able to construct the two plates, the columns, and the isolation devices in 28 days. So let's say that 1 month to design and 1 month to construct. 2 months after the earthquake, it was possible for the construction companies to build their building on top of the plates. And those 2 months were needed to go through a call for bids. Actually, there were 16 different companies who won the call for bids, and we had 16 different kind of buildings in different places and in different locations.
This is very impressive, and you discussed all this work in the recent Marit Milne lecture, the 19th
Yes.
Marit Milne lecture that you delivered in London last May. Congratulations on an excellent Marit Milne lecture.
Thank you.
And just to ask you a bit more on the discussion that you provided there, in general, what is your insight? How can we be better equipped for future disasters?
Well, as you know, the one of the focuses of the Milne lecture was how to design for big disasters in which it is reasonable and conceivable to have a large number of homeless people. Actually, I've been showing in the work I did for the lecture that this kind of problems is not common, cannot happen for a relatively small earthquake, cannot happen for a strong earthquake at a large distance, cannot happen if you don't have, let's say, a city or a large town with a relatively large number of inhabitants. So this means that with a careful analysis of the situation, in any seismic prone country like mine, like yours, like Turkey, like several others, we can reduce the location in which there is a need of looking at these kind of problems and focus on those cases only. So in a country like mine, where we have maybe 10,000 municipalities and 1,000 counties, I show that it is only necessary to look at about 50 cases and not more. And this is the one very relevant issue. A second relevant issue, in my opinion, is that you can easily think in advance and find out places in which you could conceive to build. You can find out, so you can do all the work that was done in a hurry in L'Aquila could be done in advance, and could be a work that in which it will be easier to find consensus. So you can involve the population, you can involve the decision makers, and at the end you can also think in long terms and saying, okay, we want to have the buildings for homeless in a certain location, also because we know that when they will progressively go back to their locations, we can use these buildings for students, for elderly people, to support hospitals, whatever, for other purposes. And we already can foresee which kind of, say, intervention may be needed, if any, to transform the functioning, the way of working of these buildings. I'm now trying to describe this in relatively simple words, but it's not been that simple to go through all the process to enucleate all these findings.
Yes, but it's a very important thing that you say that this is something we can be prepared for, and it reduces to few scenarios that one can consider beforehand.
Yes.
So, for our listeners, you can find the Mallet Midnight Lecture, the publication by Professor Calvi on the Bulletin of Earthquake Engineering, and you can find out more details about that. And now I want to ask you in general, Professor, how do you see the future of earthquake engineering?
This is the most difficult question that you've been asking me in this entire interview. Um, um, earthquake engineering is changing a lot in the sense that uh, we uh, we have been essentially designing to protect the lives and to avoid collapse for years. Now, in particularly in countries where this has become a tradition, maybe this is a little bit of a problem, but we are facing the fact that even if we are avoiding maybe collapse in general and we are protecting lives, the losses in terms of effects on our lives and social issues and so on is become more and more and more relevant. So I'm not saying that we should forget about the problem of avoiding collapse, but I believe that the focus will become more and more and more on the capacity of reducing the effects on society, which means to reduce losses not only in terms of monetary losses. If a university has to close for a certain time, this is not only monetary losses, is loss of culture, is loss of our normal standard state of lives. If a bridge cannot be used, it's not just a matter of taking an alternative route. It has an effect on economy, it has an effect of the way of living and so on and so forth. I think that this is one of the key issues that will become more and more relevant in the next future. And of course, going into this direction, it means that um, it will become easier to find some sort of um, similar way of thinking in different areas. I've been showing a few years ago that it is possible to somehow compare the losses that take place after a seismic event with the losses that are due to inadequate conservation of energy and protection of it's a limitation of consumption of energy and so on and so forth. Well, you can find similar metrics for so different problems, and you can show whether it is more important for our lives once you have protect collapses, where and why is more important to invest money, and what it is the possible return to society. See if this is feasible with the cost of heating and and so on. I mean, and air conditioning a building and so on and so forth. This is also feasible for to compare the problem of I don't know of the possible damage induced and losses induced by a river in case of too much rain, something that is becoming more and more common in our country, and with all sorts of different issues to our way of living. I think that these are the issues in which earthquake engineering could be a leading force in the future, because after all, we are a little bit more advanced than others.
Mhm. So, yes, you're making a very good point about how we consider other risks as well and how we need to integrate them, and then the impact on society, because, as you say, we need to remember the use of the buildings, the importance of each type of building, and all these aspects. And now I would like to come to the issue of digital technologies and AI. So this is a big topic of discussion, both in education and research. And I would like to hear your view on that. How can we make good use of AI in earthquake engineering?
Okay. Okay. The first thing that I would like to underline is that if we stay strictly to definitions, AI does not exist. I've been asking people working in this area in a bit provocative way to give me the definition of artificial intelligence. And of course, they said, okay, it is a definition provided in 1956. And this is when a software does something for which it has not been programmed. So if this is the definition, artificial intelligence does not exist because I am not aware and I have not yet listened to anybody who has been affirming that there is a software that does something for which it has not been programmed. So if we take this apart, then we should recognize that now we're using artificial intelligence with a different meaning. We are using artificial intelligence as a way of enhancing our capacity of treating data and of finding solutions due to the capacity of comparing, of understanding a large number of solutions provided to all sorts of problems in the past. This applies to the capacity of writing a sentence or writing a thesis. I've been told that many students are now writing their thesis, asking some sort of artificial intelligence to write their thesis. This kind of artificial intelligence will never produce a new idea unless it comes from the repetition of something. And of course, I'm not saying that this has a little value because I'm fully convinced that a lot of progress in humanity, actually most of the progress, came from the use of concepts developed in one field and applying them to another field. This is something that I've not yet seen used in artificial intelligence, but I think that is something that will become very useful. Maybe it is used. I'm not an expert in artificial intelligence, but you understand what I mean. Okay, let's use artificial intelligence for what it is, and let's make the best use of it. And the best use is certainly the capacity of treating large number of data to show what is the most common or the unpredictable solution. Maybe you are familiar with the meaning of a black swan that Nassim Taleb, defined years ago, and he was somehow saying that only when you look at the very extreme tails of probability curves, you will find out something that is inducing big changes in the society. If you do something like that, it means that you are looking at events that are extremely low in probability of occurrence. And in most cases, in our common way of thinking, you are not using them because you are cutting the tails of the curves. So maybe artificial intelligence could also be used for these kind of things, which is somehow the opposite of the common use of artificial intelligence. But I've been freely speaking now. This does not come from my reflections or so on. I was just answering your question out of the blue, let's say.
Yes, no, these are very interesting thoughts. And you mentioned about the use of AI by students for writing the thesis or doing assignments. So, in specifically for the education, what can we do to control that? What is your view on that? How do we deal with these digital tools?
I'm not worried about the use of a tool. I think that the students should make a better use, in the sense that there is nothing wrong in using the tools to see what they would produce, but then they will work on top of it. It's somehow accepting that even the best of the students normally should somehow walk on the shoulders of previous researchers and not pretending that in 5 minutes he could have a great idea and find out a solution. You should first start from the past and even from the far past. So the artificial intelligence could become a help in this from this point of view, provided that it is an help. And then there is something that comes from our brain, which is true intelligence, not artificial.
Mhm. Yes, you are very right in that we have always been progressing based on the previous uh, parts, so the AI can be used in that sense. With careful and critical thinking, it can be a very useful tool. And in general, any advice that you may have for students or early career earthquake engineers in academia or industry?
We already partly talked about this, walking on the shoulders of past giants is the first suggestion that I would give. Then, particularly with reference to what we are saying earlier about artificial intelligence, so on, I would say that students should not be scared to try to develop something, but be critical. Be critical. Be ready to continuously change their minds. To change minds is not a fault. Is not a sign of weakness, in my opinion. Is a sign of being humble enough to recognize that there can always be a better solution. This is not only true in saying trying to find research issues and so on, but this is also true when you are designing a new structure. So it happened many times in my life that I was designing a new bridge, a new something, and I thought that there were great things, great innovations, and so on. And then someone was showing me, well, what about this and what about that? And then you have to change the solution, and there is nothing wrong with that. So on one side, be bold, create. On the other side, be humble enough to change your mind and to go back to your
Mhm,
previous step and to reproduce it.
mhm. Yes, so be open in general to new ideas and to new approaches. Yes, that's a very good point. So we are now coming to the end, close to the end of the podcast, and we have talked a lot about your research, projects that you have been involved. And I want to ask, how has, or maybe has engineering changed the way you view the world, buildings? Um, how has this impacted your view of the world in general?
Well, first of all, for me, engineering is finding a solution. This is the first point.
Mhm,
I've seen too many people who are, you know, continuously putting problems on the table. We have problems, but we must find solutions. So someone who is only putting problems is useless. So first of all, when you come to a problem, start immediately thinking about the solution. This is my general way of thinking. Secondly, I think that the most difficult thing is to make a good compromise between uh, the tradition and what has been done in the past and what is the founding in the past with new technologies, new ideas, and so on. One case in which I've been using new technology very recently is that they were asking me about a problem with a pilot towers in the port of Genoa, designed by famous Renzo Piano, which was 80 meters tall and perfect, everything perfect, beautiful. Beauty is constructed, is finished. But unfortunately, even in a not so strong wind, the top of this tower was moving with an acceleration which was not acceptable for the human body. So can you imagine a new pilot tower where you have people at 80 meters above the sea level to watch around, and where maybe 60 days per year people have to come down because they are somehow sick because of the acceleration? And I used four active mass dampers with an acceleration of only 300 kilos each, with an acceleration capacity of about 1 g each one, and with a displacement of about 1 meter. But what is interesting is that the company who developed these devices was using orientation of magnetic field to accelerate the mass, which means that the need of energy was quite low uh, for all this process, and therefore it was possible to guarantee the permanent presence of electricity even in absence of the electricity coming from outside and so on and so forth. And I had a very funny experience when I took a few people to the top there and I said, look, now one of our masses will act as the bad guy. So instead of stopping the movement, it will try to accelerate the tower, taking it to resonancy and to go to the maximum possible displacement. And it was really a problem of feeling sick and so on. And now I said, look, we will keep one as the bad guy, and the other three will try to stop the tower. So one will become as an excitation mass, and the other three will try to act as a stopping masses. And it was a lot of fun because actually they were capable of stopping essentially the tower, and they're now operating. So I'm sorry, I've been very long, but I'm trying to say that I think that the combination of new advanced technology with traditional way of construction is somehow a combination of art and science, is a combination between experience and intelligence. So it's the best possible combination of our being engineers and designers.
The art of seismic design, as you mentioned in the World Conference, right?
Yes. Yes, exactly.
Good. So my last question, Professor, what are your plans for this period and next steps you want to focus on?
I'm close to retirement, So now I am working on some large design problems now. I've been working recently on a few, actually 13 new bridges in a freeway in northern Italy that has been very challenging because of problems on maintaining the freeway in functioning while you were working and so on and so on and so forth. And this has been quite interesting. And I am trying to continuously work with the, say, my successors at the Law School and at Eucentre. But I think that it is our duty as person who are close to the end of their career, not to be too invadent, too disturbing. We have to keep our role, and I've been trying to pass whatever I could to younger people because I think that this is what we should do. To not to try to be remaining sitting on the same chair till we are 100 years old. I'm also working with Eucentre and others on other interesting projects. We are somehow been designing the reconstruction of an entire village which was destroyed by an earthquake. And in my idea, this entire reconstructed village will be completely seismically isolated. So it will be the first example of an entire town completely isolated. So these are the things that I.
Okay, yeah, this sounds very interesting. Good. Okay, so thank you very much, Professor Calvi, for everything that you shared with us today. It's really appreciated, and I'm sure that our listeners will benefit from it. It was a great pleasure having you with
It
us.
has been a pleasure to discuss with you. You have been a very good and intelligent question makers.
Thank you very much.
Questions maker.
Thank you
Thank
very
you.
much, Professor.
Thank you.